So let's see what we can do with these continuity equations that I'm trying to convince you are useful. We're going to take a very, very simple problem. And this problem is we have two rivers that are side by side. This is plan view, right? So here's one river, here's another river. And the heads aren't changing much in those rivers. Rivers are mostly flat. And so we have basically constant head along here and constant head along here. And this is head 1 and this is head 2. So then take a section through that. We're going to see that these two rivers are joined by a confined aquifer. So we're really vertically exaggerating this, of course. And so there's the head in the first river, and here's the head in the second river. And you can see the confined layer here and the confining layer down here. We have our aquifer in between, right? So we have flow from high head to low head, so we've got flow going through this aquifer from this direction to this direction, right? So what we want to do is we want to find an equation for the head in this aquifer. That basically we know here the head has to be equal to the river. We know here the head has to be equal to this river. But we don't know what that head looks like in between. So let's see if we can come up with an equation for that. And we're going to start with our continuity equation. And we only need one dimension of that continuity equation. So, even though we have, I'll write it all out just so you can remember, even though we have an equation that works in 3 dimensions, now remember this is confined, not unconfined, so we don't have h squared, we have h. So here's our total continuity equation, but we're going to work in steady flow. So we're going to solve this for steady flow. So the first thing that we can do is this. So steady, that equals 0. And then since we're only working in one direction, let's call it the x direction, we don't need this. These are 0 as well. And so now we've got this equation that's simply the second order partial derivative with respect to h is equal to 0. Right? So this is a one-dimensional form of the Laplace equation. So we have the second order derivative, and what we want is h. So how are we going to do that? Well, we need to integrate twice. To find h. Right? So if we integrate once, we have partial h with respect to x. Actually, now we can get rid of the partial because we're only working with one variable. So no need to use the partial. Oops. No, that's right. So we integrate once, and we have a constant on this side. And then we integrate again, and we have h as a function of x is equal to ax plus b. Okay? So we have these two constants that came out of the integration, and we need to find those. And we find those by applying our boundary conditions. But look what we already know. We know that the head is ax plus b, and we know that this is the form of a straight line. So we already know that this head has to be a straight line, and we know that it's connecting these two heads here. So we already know that the head is going to look something like this. We haven't even solved anything yet. So now we have the general equation of flow. We know that the head has to be a straight line, but let's go ahead and find out what that equation would be. We're going to do that by solving for these two constants by applying the boundary conditions. So we need to solve for the constants, a and b, and we can do that where we have h at x is equal to 0 is equal to h1, and when x is equal to 0, that's equal to b. So b is equal to h1. And then we have h at x is equal to l is equal to h2. But we see that's a little bit more complicated. We have A times X plus, we've already solved for B, so we can put in H1. And so A is now equal to, this is where this is L, right? This is L now. And so we can solve for A, and that's going to be H2 minus H1 over L. And then that means that we have H of X is equal to H2 minus H1 over L times X plus H1. So now we have our equation for the head through this entire formation, used symbolically. And in fact, you can see that it's a straight line. This is a constant, this is a constant. But now we know what the values are for anywhere head in this confined aquifer. So this is a very simple application of how we can take a pretty complicated continuity equation, apply the situations of the particular problem. Is it steady? Is it transient? Is it 1D? Is it 2D? Is it 3D? And then apply the boundary conditions and produce a model for hydraulic head. Where we substitute in, if we substitute in this expression here, notice we have this expression for time and we have this for head. And so when we substitute this in, we end up with the specific storage times the change in head with respect to time. And so this is our continuity equation that accounts for flow in and out of that control volume. And so we have water flowing in and out of the control volume, and then we have water coming from storage. And remember, S sub S is specific storage. So we're going to play with this a little bit, but this is the starting point.